the theory session early this morning. We have an awesome lineup coming up. Just to keep things started, there's a tight schedule as always, so I'm just going to get it started. We're going to start with 4 spotlights, then we have 1 oral. It's a very cool oral. You should stay for it. And then there's 5 more spotlights, and that's it. So we'll kick it off with the first round of spotlights. Here's Sofyan. Oh, actually, let me make an announcement. Please don't stand in the back. There's some fire code violations. So between timing, I'll have people come to the front.
Thank you. Hello, everyone. I am Sofyan from University of Lyon, and I'm presenting to you the main ideas of our paper, Revisiting Epsilon Gamma Tau Similarity Learning for Domain Adaptation. So this is a joint work with Yevgen Redko from University of Saint-Etienne. And I'll first introduce the main 2 aspects of our work's context, which are similarity learning and domain adaptation. So it is known that several machine learning classification algorithms rely on some similarity function in order to produce a classifier. We can think of SVMs and nearest neighbor classifiers as examples. And the need to improve these algorithms has led to the emerging field of similarity learning, in which the similarity function is learned from the data rather than being a generic one, such as the dot product or the kernels. And while most of the work in this area was done in a supervised setting, we analyze this area in a domain adaptation setting in which we have access to a labeled source sample and an unlabeled target sample. And we would like to make predictions over this target sample. So the 2 samples are coming from, typically coming from 2 different probability distributions. And among several classes of similarity functions, we are interested in epsilon, gamma, tau good similarities, which are theoretically well-founded, and they capture the fact that most of the points are closer to landmarks of their labels than landmarks of other labels by a certain margin. So landmarks can be seen as good representatives of their respective classes. And the good thing is, using such a similarity function, one can map the data into a space where it is linearly separable. And this of course reminds us of the similar result for kernel SVMs. It can be seen as a generalization. And in the literature, there are several algorithms that minimize the epsilon and thus learn the similarity. Now, concerning our work, we begin by slightly modifying the previous definition by allowing the landmarks to come from eventually another distribution. We can imagine wanting to include some target points, labeled target points in the landmarks. And the main question that we ask is, if we have a similarity that is good on the source domain, how will it behave on the target one? So this is the main result where we prove that the performance characterized by the error of the similarity function on the target is multiplicative on some divergence term. And it depends whether the source distribution dominates the target one. And in the case when the source distribution dominates the target, then we have a multiplicative dependence on the epsilon on the source domain, meaning that a low error on the source can compensate the divergence between the 2 domains. Finally, we wanted to test these bounds, so we generated a synthetic data set that is the mixture of 2 Gaussians, each component representing a class of interest, and you obtain the target domain by rotating the source domain around the origin by an angle going up to 90 degrees. So the greater is the angle, the harder is the adaptation. So that's what we see on the figure on the right, when the divergence between the 2 domains increases as the angle increases. And the 2 figures to the left show that by minimizing these bounds, we obtain better results on the target domain. So if you are interested in more details about the bounds and about the numerical implementation, You are welcome to visit our poster number 152. Thank you.
Hi, my name is Michał Derezinski. I'm at UC Berkeley. This is joint work with Manfred Warmuth at UC Santa Cruz and Daniel Su at Columbia University. I'll be talking about leveraged volume sampling for linear regression. So we study the standard least squares regression problem. We're given a sort of a data set represented by a matrix X with n d-dimensional input vectors, which are rows of this matrix. The loss below is the square loss, and the optimum W star is the least squares optimum for this problem. So, of course, we have response vector Y. Those are real response values, one assigned to each input vector X. So what if the response values are hidden and they're sort of expensive to compute? We wish to only compute a few of them. So our setup is that we're going to sample a few input points X for which we're going to receive responses Yi, and we would like to sort of approximately minimize the loss. So our goal will be to find the best unbiased estimator for this task. So what does that mean? So we want to design a sampling distribution over the subset of input vectors we choose and a estimating function W hat, such that in expectation under the randomness of the sampling, our sampling, the estimator is unbiased estimate of the optimum, of the least squares optimum coming from sort of the solution of the whole problem. And at the same time, we would like the estimator to have a sort of a relative loss bound that is only 1 plus epsilon larger than the loss of the optimum. So again, very simple setup. We have a least squares regression. We sample subset. We want the best unbiased estimator. So at first glance, it appears that this problem should have been solved long ago. But surprisingly, that's not the case. And the reason is that most standard sampling methods for this task do not give you unbiased estimators. So for example, the standard method of leveraged score sampling, which is sort of an IAD sampling method, which samples one row at a time IAD, has to produce biased estimators. So recently, sort of last year, we showed that there is a joint sampling method which samples sets of input points jointly in such a way that you can produce unbiased estimators for this task. So basically, the prior work situation was that we had leveraged score sampling, which is biased but gets very good loss bounds, and volume sampling, which is unbiased, and it was not clear what kind of loss bounds we can obtain in terms of this 1 plus epsilon type guarantee. So what is volume sampling? Volume sampling, we're sampling a subset of indices of fixed size k, and each subset, the probability of sampling it is proportional to the determinant of this sample covariance matrix coming from that subset. That's a D by D matrix. And the name comes from the fact that the determinant can be interpreted as the volume spanned by the vectors. This is the right intuition, is that sort of the vector should be well spread out in the space, in the RD space. And for this distribution, last year we showed that, in fact, if you simply solve the subproblem designed by the subset S, then the obtained estimator is, in fact, an unbiased estimator for the least squares solution over the whole problem. But unfortunately, as we show in this work, if you want a loss bound, a particularly accurate loss bound from volume sampling, you may need a very large sample to achieve it. If particularly if epsilon is less than 1/2, this was sort of surprising to us. You may need even half of the samples of the whole data set, which sort of comes. So it comes from the fact that, in some sense, leveraged scores do not if there's points in the data that sample that have very high leverage scores, volume sampling may miss it. So we sort of, our idea is to combine IID sampling and volume sampling together, and we show that this achieves unbiasedness and 1 plus epsilon loss bounds. And finally, we actually show that leveraged volume sampling can be computationally much more efficient than volume sampling itself, and we show experimentally that it performs better than both leverage score sampling and volume sampling. So for more details, check out our poster on number 151. Thank you.
Thanks everyone for coming. So this is about our paper, Synthesized Policy for Transfer and Adaptation Across Tasks and Environments. To begin with, let's consider a following example. Suppose that we are building a real-world household robot. We will expect to have such a robot that has multiple functionalities, for example, mopping the floor, washing the dishes, and cooking. At the same time, we will expect such robot can function on multiple environments, for example, different apartments with different layouts and decorations. Traditional reinforcement learning would typically require to learn an agent in all combinations of environment and tasks, which is costly and inefficient. In this work, our goal is to develop an algorithm that can learn within a minimal subset of environment and task combination, such that it can generalize to all combinations. We explicitly decompose the environments and tasks for transfer learning and describe 3 progressively more difficult settings. The first setting describes a zero-shot compositional transfer. Here, the red dots are the same environment and task combination, and the green dots as unseen ones. Through combining knowledge from previously encountered environment and tasks, we can achieve transfer to new combinations. In the second setting, we incrementally learn about a brand new environment and a brand new task to achieve the generalization. And in the last and the most challenging setting, we simultaneously learn about both new environment and new tasks to achieve the same goal as before. Next, we describe our proposed model for achieve these 3 different settings in a unified manner. The main idea is to synthesize a policy as a linear combination of a shared policy basis for different tasks and environments. Consider we have an MDP that is defined by an environment and task combination. First, we extract state feature and action feature using neural networks. Next, given the indices of environment and the tasks, we retrieve their corresponding embeddings and then feed them into a compositional network to generate the policy coefficients. Then, using these policy coefficients to combine with a 3-dimensional policy basis, we can generate a bilinear policy mapping, which is then used to combine the state feature and action feature for computing their score. To facilitate the learning of this process, we also use an auxiliary loss to train our embeddings. Next, we describe our experimental settings. We study on 2 different simulators with roughly 400 combinations of environment and tasks. And for each of them, we train on 144 and test on the rest. In the setting 1, our algorithm outperforms all the baseline and previous methods. Likewise, in setting 2 and 3, we achieve the same superior results. For more details about our paper and methods, please come to our poster, number 155, at 5th floor. Thank you.
Hi, thanks for coming. I'm Ainesh Bakshi, and I'll be talking about sublinear time low-rank approximation of distance matrices. This is joint work with David Woodruff. We're both from Carnegie Mellon. All right, so why should we care about low-rank approximation? It is the method of choice for data and matrix compression. It is also used as a pre-processing step for denoising and dimensionality reduction. It has numerous applications to clustering, topic modeling, recommendation systems, and distribution learning. All right, let's begin with a formal definition of what low-rank approximation is. You're given as input an n by n matrix A and an integer k, and your goal is to find a rank k matrix X that minimizes the Frobenius norm error. Note, because of this rank constraint, this is a highly non-convex problem. Pictorially, you're given a square matrix A, and you want to factor it into two matrices, U and V, such that their inner dimension is k. Typically, k is a lot smaller than n. All right. Now let's define distance matrices. You're given a set of n points in d dimensions, and the distance matrix just represents all pairwise distances between these points. For instance, the ijth entry of matrix A is distance between point pi and pj. Note the distance here can be any arbitrary metric. Also, such a matrix is dense. It has order n squared non-zero entries. All right. Even though this problem is highly non-convex, it's quite surprising that there exists a polynomial time algorithm to actually compute it optimally. And this is the famous singular value decomposition algorithm. What is it? Given a matrix A, you decompose it into three matrices, U, D, and V, such that U has orthonormal columns, V has orthonormal rows, and D is a diagonal matrix. In order to get a rank K matrix out of it, you look at the diagonal matrix D and you truncate all but the top K singular values. Now you have a rank K matrix, and turns out this is optimal. It solves the low-rank approximation problem optimally. However, the running time is n cubed. And this is too slow for large data sets. So the obvious question is, can we do better? It turns out in 2013, Clarkson and Woodruff showed that you can actually output a rank K matrix P that obtains a 1 plus epsilon approximation to the optimum cost. And the running time is now n squared plus n poly k over epsilon, where the second term is usually a low order term, since k and epsilon are typically small. Note the first term is just the amount of time required to read the input. For many real-world applications, this might still be too slow. So the main question that we answer in this research is, can we actually leverage the structure of our distance matrix to get faster algorithms? Surprise, surprise, we can. So what we show is that we can actually output matrices in factored form, U and V, such that the product is a rank K matrix, and we get an additive error epsilon approximation to the optimal cost. And the running time is almost n. It's n to the 1.001 times poly k over epsilon. So this is surprising because we do not read most of the input, and we are still able to get a low-rank approximation. For practical problems where computing the pairwise distances between points is costly, we show that we only need to read a very small fraction of the input. So we need to compute a very small fraction of these pairwise distances. So here's a comparison of all three algorithms that I mentioned and their theoretical running time. We started with an n-cubed algorithm. We got it down to an L-squared algorithm using Clarkson-Woodruff. And in this work, we leveraged the structure of distance matrices to get an almost n-time algorithm. We then run some experiments, and it turns out the experiments match our theoretical guarantees. As you see, on a clustering data set and on an MNIST data set, the running time decreases following the theoretical bounds. Finally, we do some experiments comparing the absolute error. So note the SVD given in blue is optimal. Our algorithm given in red is fairly close to the optimal. That's my time. Thank you.
So that was the first round of spotlights. Let's just give another round of applause to all the spotlight speakers. And we have one oral in this session, and this oral is one of the winners of the Best Paper Award. The talk will be given by Chris Liaw. So I have some mysterious envelope, which I believe contains the award, and I'm going to give it to Chris, and let's just please join me in congratulating Chris and all the authors. And Chris will be talking about nearly tight sample complexity bounds for learning mixtures of Gaussians.
Okay, so hi everyone. It's certainly an honor to receive that award. I've enjoyed many of the talks here, and a lot of them are probably equally deserving. So this is joint work with my co-authors, Hassan Ashtiani, Shai Ben David, Nick Harvey, Abbas Moravian, and Yaniv Plan. And without their hard work, this project would not have been possible. So the problem that we look at in this work is that of density estimation. So in this problem, there's an unknown distribution D from which we can draw IID samples from. And our goal is to design some algorithm that will take these samples as input and output some distribution D hat that is as close to the unknown distribution as possible, let's say in the L1 distance. So this is a very fundamental problem, and it's been studied for well over a century. And possibly one of the most fundamental questions you can ask is how many samples do you need from this unknown distribution in order to get a good approximation to it? And such a question is very important in practice because you can imagine that drawing samples from this distribution can be very expensive. For example, it might require sequencing a person's genome just to get a single sample. So in fact, Dai-Kanikla has posed an open problem to try to better understand the sample complexity for density estimation. And more specifically, he asked whether there is some notion of complexity which will completely characterize the sample complexity of F, of some class F. And there's been a lot of work recently on trying to get tight bounds for various classes. And this work will explore tight bounds for a very fundamental class, which is that of mixtures of Gaussians. So let's start off with the simplest case, which is just a single Gaussian in d dimensions. So as many of you know, there's a very simple algorithm for this. If you want to try to get some error epsilon, say in L1 distance, then you simply draw d squared over epsilon squared samples, compute the sample mean, and compute the sample covariance matrix. And this is, with high probability, this will give you a very good approximation. Actually, this bound here is quite intuitive. A Gaussian in d dimensions has d squared parameters, and the 1 over epsilon squared seems necessary just to deal with a sampling error. So what about mixtures of k Gaussians? Well, here there are kd squared parameters, so the naive guess is that kd squared over epsilon squared sample should suffice. So actually, prior to our work, this has remained unresolved, and is one question that we resolve in this work. Some previous work of my co-authors did get close to this bound, but they had a suboptimal factor of in epsilon. So sort of motivated by this gap in our understanding, this work, the main goal of this work is to introduce a new technique for density estimation. And one of the philosophical inspirations for this new technique is this idea of Occam's razor. And that is, if you have multiple explanations for some phenomenon, then all else being equal, you ought to search for an explanation that is simple or that is very short. And this sort of ideology has had many manifestations in learning theory over the years. And one such example, which sort of inspired some of our ideas, is this sample compression idea due to Littlestone and Wormuth, which they introduced to understand classification. So in the density estimation, this work introduces a notion of compression, which we then use to obtain a new technique for density estimation that is not only very simple to use, but promises to be sample efficient as well. And the main application of this new technique will be an improved upper bound for the sample complexity of mixtures of Gaussians. And in fact, we'll show that kd squared over epsilon squared samples suffice. So it matches what we would naively guess. And we also show a nearly matching lower bound. And just as a reminder, the tildes on top of the O's and omegas are hiding polylog factors. Okay, so let's talk a bit about compression. And let's start off with a very simple example just to get an idea of what compression is. So here I have a Gaussian distribution, a one-dimensional Gaussian, with mean mu and variance sigma squared. And in the compression framework, we always begin by drawing a small number of samples. So here we're drawing a small number of samples. And the goal of compression is to try to encode this distribution somehow using as few of these samples as possible. So that seems like a somewhat mysterious task. Let's just look at one possibility of how to do this. So observe that if you draw a modest number of samples, there must be a point that's really, really close to mu minus sigma with high probability. And there must also be a point that is really, really close to mu plus sigma with high probability. So let's just single these 2 points out, and let's just give them to someone. And now what can they do with these 2 points? They can try to compute the mean. And if you look at this picture, the mean is really, really close to the mean of the true Gaussian. And if you look at the distance between these 2 points and divide that quantity by 2, then that turns out to be really close to the standard deviation. So in other words, if someone had just these 2 points, they can actually recover an approximation to this Gaussian. All right, so the more general comprehensive framework is as follows. First, let's fix a class F of distributions. Think of F as being a Gaussian or the class of mixtures of Gaussians. And there are 2 parties here, Alice and Bob. So Alice here knows the class F, but she also has a distribution D in mind. Bob only knows the class F. The goal is for Alice to communicate her distribution to Bob in some way, but in order to make it work for density estimation, we have to restrict the kind of communication Alice is allowed to do. So what she's allowed to do is as follows. First, she can draw some samples from the distribution, and then she can look at these samples and try to find some representative points. She'll then send a small subset of these points to Bob. These points are known as a compression, and Bob will take the points that he receives and try to construct some distribution out of it. So if it turns out that Alice can send only T points to Bob, and Bob can reconstruct a distribution that's actually close to Alice's distribution, then we'll say that the class F has a compression of size T. So one of the key insights in this work, or one of the key results in this work, is a connection between compression and learnability in a density estimation setting. More specifically, if you have a compression scheme of size T for some class F, there's actually a black box that you can plug this compression scheme in, and it'll output an algorithm for learning any density in F, say up to L1 or epsilon, with only T over epsilon squared samples. So in other words, as long as you can succinctly describe any distribution in some class, then that automatically gives sample-efficient algorithms. And let me just give 2 sentences of the proof. So the idea is that if you have a compression scheme, then you can find a very small set of representative distributions. And if you're familiar with the literature, then think of this as an epsilon net. And now you've reduced to learning a finite class for which we know how to do. So the main goal is to design efficient compression schemes. So one very nice property of compression is that it extends very, very nicely to mixture distributions. So let's see why this is using another example. So here I have a mixture of 3 Gaussians. They could all have different mean and different variances. And just for simplicity, let's assume I have a uniform mixture over these 3 Gaussians. So as always, we draw a small number of points. And the main idea for compressing mixtures is that we already know how to compress each component. So let's just compress each component of the mixture separately. So for example, for the blue Gaussian, we already know a 2-point compression scheme for the blue Gaussian. So let's just use that. And similarly for the green Gaussian and the red Gaussian. So this gives a compression scheme of size 6. And more generally, if you have a class F with a compression scheme of size T, that automatically extends to a compression scheme for the K mixtures of F. And the compression scheme only uses about KT samples. Okay, so now that we know that if you can compress a class, you can compress mixtures. And the very fact that you can compress means that you can learn. And so one of the main theorems in this paper is the following. If you have a compression scheme of size T for some class F, then there's a black box which will take that compression scheme and it'll output an algorithm that learns K mixtures of F using only KT over epsilon squared samples. So we found it a little interesting that compression actually extends nicely to mixture distributions. And it'd be very interesting to see if such an analogous statement holds for other notions of complexity, maybe something like VC dimension. Okay, so let's see how to get an algorithm for learning mixtures of Gaussians. And using our compression idea, it suffices to design a small compression scheme for just a single Gaussian. And in the paper, we show how to do this using some geometric intuition. Recall that a Gaussian, if it has a mean mu and covariance matrix sigma, then we can represent that as an ellipsoid whose center is at mu and whose axes correspond to the eigenvalues and eigenvectors of the covariance matrix. So to encode a Gaussian distribution, it suffices to somehow encode the ellipsoid. So here I have a 2D example just to get a sense of how to do it. Actually doing it requires a bit more work. So again, you draw a small number of points. And the idea is that if you wanted to encode, say, the axis V1, you can try to do that using a linear combination of some of the drawn points. And similarly, you can do something, you use a linear combination for some to approximate V2. So for example, the average might work here. And more generally, if you're in D dimensions, then each of the axes can actually be encoded with about D of the sample points. And since there are D axes to encode, this gives you a D squared compression scheme. Okay, good. So once you get a D squared compression scheme, then this immediately extends to an algorithm for learning mixtures of K Gaussians. And moreover, it uses only KD squared over epsilon squared samples, at least up to some polylog factors. And so this improves upon some of the previous work in bounds that we know of. For example, it improves upon a VC dimension argument, and it also improves upon the work done by my co-authors. And moreover, this is nearly tight. So we do show a KD squared over epsilon squared lower bound. This is a bit technical for this talk, but it uses ideas from information theory and high dimensional probability. And these compression ideas do extend to agnostic setting as well. So there's no reason to assume that the actual distribution is a mixture of Gaussians. So let me just summarize the talk. So here we introduced a compression framework density estimation, and we saw that it's quite powerful. It gave almost nearly tight upper bounds for learning mixtures of Gaussians. And it'd be interesting to see how far we can push these compression ideas. So whether or not we can apply, or to see where, to see this compression idea applied to other problems in density estimation as well. And our algorithm is currently not computationally efficient. It'd be interesting to see if we can get an algorithm that's more computationally efficient as well, or even if the framework can be made more computationally efficient. And just to finish off our results, we have a nearly matching lower bound. So if you want to know more, we'll be at poster 100. And thanks.
We have time for 1 or 2 questions.
So very beautiful work, but it seems like you try then, once you have a compression scheme, you try all possible ways to build a mixture and pick the best one, right?
Yes.
So what is still your favorite efficient algorithm?
My favorite efficient algorithm? Good question. There's this, I mean, for density estimation, there's one by Suresh, which is quite nice, the one that I mentioned. Uses some clustering techniques, uses Chefet. Yeah, it might be interesting to try to use some of those techniques to try to make ours efficient as well.
Yeah, can I ask another question? So I was studying Gaussian mixtures, but I'm just wondering if the two clusters are very close, like the cluster means are close, does that affect the sample complexity?
So at least on the upper bound side, no. So I should mention that our work doesn't care about any separation at all. It can be close, it can be far, and we'll get the same sample complexity, or the same upper bound.
Okay, thank you.
I just want to add a clarification. I mean, that the point is that we're not doing parameter estimation. We are estimating the probability distribution. So of course, if the two Gaussians are close, you cannot separate the means, but we don't care about the parameters, we just care about total variance approximation. So the separation doesn't matter.
I still don't quite understand. So if they are very close,
I can output one Gaussian rather than two. If it's close in the L2 distance, I'm in L1 distance, I'm doing fine, I don't care about it.
So using one cluster, it still has small error.
Exactly.
Is that what you mean?
Exactly.
Okay, thank you.
So I actually have a related question. So I like total variation, but can you say anything about like maybe other people like KL and these kind of things? Is that easier? Or?
So KL is a bit not so nice because if you imagine a really small component out way off in infinity, like away from your other components, then you have huge KL.
Yeah.
But you have to draw so many samples just to find that one small component And
Cool.
yeah.
Okay, let's thank the speaker again. And now we have 5 more spotlights. And the first one is Jae-Ho Lee, as soon as we get set up. Cool.
Hello, everyone. This is a joint work with my advisor, Maxim Roginski. The minimax statistical learning, as opposed to classical statistical learning, is about finding a hypothesis which minimizes the worst-case risk over a set of distributions instead of just a single distribution. So this set of distributions that we call the ambiguity set is designed to represent some inherent uncertainties that arise from the practical machine learning problems, such as domain drift, where we expect that the training and test data are drawn from different distributions, or adversarial perturbations. And the natural approach to solve this problem, when we have like an access to NIID drawn copies from the target distribution, is that we can minimize the empirical version of this worst-case risk. And then the natural question to ask is, what is the speed of convergence of this, what we call minimax ERM hypothesis? What is the convergence rate of the excess risk of this hypothesis to its theoretical optimum? So in our work, we focus on the ambiguity sets taking the form of one Wasserstein balls, but we actually do p Wasserstein balls. But yeah, for now, let's just talk about one Wasserstein balls here. So the main theoretical challenge here is to tame this behavior of this suprema over the probability distributions. And the trick we use is to write down the dual form of the worst case risk as an infimum over the dual parameter space lambda, minimizing the expected value of some dual function with respect to the dual parameter lambda and the hypothesis f, taking expectation with respect to the center of the Wasserstein ball, the distribution at the center of the Wasserstein ball. And then we can view the minimax ERM as a joint minimization process over this dual parameter space lambda and hypothesis space f. And then the ideas from the classical machine statistical learning theory tells us that there should be some term proportional to the complexity of this joint hypothesis space and the joints and the space of the dual parameter lambda. So if we gauge the space of the complexity of the space of all these dual functions, then we can tell something about the excess risk. So here's a quick result. So under very, very mild assumptions and with high probability, this excess risk bound behaves as a sum of two different terms. The first term is the usual term in the statistical learning theory that is proportional to the complexity of the original hypothesis space and proportional to the 1 over square root of n. So this second term here is the key term, what we actually lose from considering this minimax type of formulation. So the second term behaves inversely proportional to the Wasserstein radius rho and is also proportional to the 1 over square root of n. So this term as a whole vanishes to 0 as the sample size grows. And the key remark here is that this type of result does not really require any type of harsh assumptions on the hypothesis space F, such as assuming that all hypotheses in it are L-Lipschitz or anything like that. But instead, the minimax ERM procedure somehow automatically finds the right hypothesis with enough smoothness inside it. And the next step would be to apply it to the domain adaptation problems, but I do not have a lot of time. So could you, if you could come to my poster at number 86, and hopefully we can talk more about it. Thank you for your attention.
Hi, I'm Vitaly Feldman, and this is joint work with Jan Vondrak. We'll be looking at one of the most basic questions in learning theory. How well does a model output by a learning algorithm generalize to the distribution from which the dataset was sampled? The most common approach used for understanding of generalization is based on various notions of capacity of the set of models that may be output by the learning algorithm. This is a very powerful technique, but as we now know, it cannot give tight bounds in some of the important settings in machine learning, such as stochastic convex optimization. And it turns out that our best bounds in this setting are based on algorithmic stability. So motivated by these problems, we give better generalization bounds for one of the key notions of algorithmic stability, and then apply those bounds to a stochastic convex optimization. So to make these results a little more formal, let me introduce a bit of notation and definitions. So our algorithms are running on a data set S that consists of n points that are sampled id from some distribution P. And we are also given a loss function L that measures the loss of the model on any data point. And the key quantity that we'll be interested in is the generalization error or gap for a model output by the algorithm, which is denoted by this delta S, and it is, as usual, the difference between the expected loss of a model on the distribution P and its empirical error on dataset S. So we'll be focusing on the notion of stability referred to as uniform stability that was introduced by Bousquet and Eliseev. And informally, this notion of stability bounds the effect of each of the point in the data set on the loss of the model over the entire domain. So more formally, we say that A has uniform stability gamma with respect to loss L if for all pairs of datasets that differ in a single element and any point in the domain, Z, the losses of the model's output on this pair of dataset on any point on the same point Z differ by at most gamma. There's a very strong notion of stability, but we know that it's satisfied by some important algorithms, for example, by the minimizer of the empirical loss in the strongly convex case, and also by the output of various versions of the gradient descent in the smooth and convex case. The specific value of stability parameter depends on the setting of the parameters in this algorithm, but you should think of it as being roughly 1 over square root of n after all the normalizations. So let me briefly review what's known about the generalization properties of uniformly stable algorithms. But for this purpose, let me normalize the loss to the range 0, 1. And you should think of the stability parameter as being in the range from 1 over n to 1 in this case. A classical result which is worth keeping in mind is the result of Rogers and Wagner, who proved that the expected value of the generalization error in this case is at most gamma. So the bound itself is very strong, but it's a bound in expectation on a quantity that might be negative. So it doesn't say anything about the typical value of generalization error. This issue was addressed by Bousquet and Eliseev, who showed that the generalization error with high probability is at most gamma times square root of n. So this is a bound with high probability, but this additional factor of square root of n implies that we cannot get useful bounds out of this result in many typical settings of the stability parameter. So in this work, we give a new bound on generalization error, which states that the generalization error with high probability is at most square root of gamma. To compare those results, it would be easiest to just quickly look at this graph. And as I mentioned, you can see that for our results, we get a non-trivial bounds on generalization error for the entire range of the stability parameter gamma. We also look at the second moment of generalization error, and here the best previous result is essentially based on the result on the classical work of Devroy and Wagner, which says that the square root of the second moment of the generalization error is upper bounded by square root of gamma. And we improve this result to gamma plus 1 over square root of n, which is actually a tight bound in this case. Let me briefly mention what else can you find in the paper. First of all, the most fun part, I think, is the new proof technique, and you should definitely check it out if you like concentration inequalities. We also describe our application to stochastic convex optimization. And finally, we have some connections to learning with differential privacy. Thank you.
Okay, hi, I'm Aditya, and this talk is about anomaly detection, which understood informally is the problem where given a number of instances, for example, images of road signs, we'd like to identify those instances which are in some way unusual, just deviate from some systematic pattern we believe is present in the data. To formalize this, we might imagine that our data comes from some distribution P, and that anomalies are simply points that live in a low-density region. Equally, we could think of trying to classify whether a point is more likely to come from our data distribution or a uniform background distribution. To make this a little more precise, let's say we pick some threshold alpha on the density values. Then we simply need to minimize a suitable cost-sensitive loss to distinguish between our data distribution as the positives and the background distribution as the negatives. This is a very elegant and appealing reduction, but there are maybe a few challenges when it comes to applying this for the anomaly detection. On the technical side, to even compute the loss on the background distribution, in general might require some form of sampling, which could be not ideal. In fact, even picking the density threshold alpha would require that we have some knowledge of the scale of the underlying density, which again is not ideal. And more broadly, this approach would not guarantee that we actually get confidence scores as to the degree of abnormality of a particular point, which might be useful if you want to use our anomaly detector for some downstream processing. In a nutshell, in this work, we look at how modifying the underlying loss function can mitigate each of these issues. So just to give some hints as to how we do this, to start, we've seen that by minimizing a single cost-sensitive loss, we effectively obtain a single sublevel set of the density, which can tell us if a point is anomalous or not, but doesn't give us a confidence score. One thought would be to, instead of minimizing a single cost-sensitive loss, what about minimizing all possible cost-sensitive losses? Let's take a weighted combination of all of them. So this intuitively should give us somehow all possible sublevel sets, or equally give us the underlying density. Now this might seem like a somewhat exotic object or exotic loss function, but it actually turns out to be fairly well studied in statistics under the term proper scoring rules. So we could try and apply one of these to our problem, but it actually may be more appropriate to look at a loss which only gives us the tail sublevel sets, because we may only be interested in modeling the confidence scores for points we believe to be anomalous. So it turns out, it's not hard to show that if you start off with one of these proper losses, which is suitable for estimating the entire family of sublevel sets, and now you try and restrict it to only give you the tail sublevel sets, it suffices to simply clamp the loss at a particular value, and that value is the threshold of the density. So this encompasses, again, all possible proper losses. So one of many possible examples of this would be a loss which starts off as being linear for the positives and quadratic for the negatives, which after applying this simple kind of clamping, you get a hinge for the positives and a clamped quadratic for the negatives. Okay? It actually turns out you can drop the clamping on the negatives without too much fuss. This would give a nice convex objective, but we still have the problem of finding a good value for alpha. Here, it turns out that we can actually try and optimize for alpha by adding an additional term. This term just comes from the pinball loss, which is used for estimating quantiles of distributions, and turns out to be very nicely related to the hinge loss, which was our loss on the positives. Okay, so that leaves the first issue, which was trying to estimate the loss on the background distribution. So at least for this particular example, upon further inspection, this is just the L2 norm of the function that we're trying to learn. So it kind of has a feeling of a regularizer and can be more explicitly contrast to a Hilbert space norm that we'd encounter, for example, we were using a kernel method for our underlying f. Now, interestingly, it turns out in the point process literature, it's been observed that the sum of a L2 and Hilbert space norm is also a Hilbert space norm, just in a modified Hilbert space. So what this means is that we can just use a Hilbert space norm, which has a dual role of acting as a regularizer and a background contrast. And that gives us our framework for anomaly detection, where we have a general proper loss being capped and minimized on the data distribution, a Hilbert space norm, which has kind of this dual role as model capacity and background contrast, an additional term which acts as some form of quantile control. Happy to talk more at the poster. Thanks.
Hello, everyone. My name is Jessie Finacaro, and today I get to present a result with my advisor, Ralph Anguilo, which is a first step in characterizing convex elicitable properties, and hopefully by the end of this, you will have some idea what that means. And so to start off, we're going to talk about empirical risk minimization, which many of you are familiar with. But in machine learning, we want to make some prediction Y about a future event, and we do this based on measurements in the real world X. And one of our most popular algorithmic approaches is to minimize our empirical risk. And in that sense, we get some training data, and we fit a hypothesis function, H star of X in this case, that minimizes our total loss over all of the training data. And if you look at the equation, you can easily imagine that our hypothesis, H star, can easily depend on the design of the loss function L. And so what we're interested in here is designing consistent loss functions, which will be formalized by our definition of elicitable properties. But roughly what we mean is that we want to be able to design a surrogate loss that is minimized by the same hypothesis as our original. And so just for a concrete example, many of you are, hopefully all of you are familiar with 0-1 loss and the issues that arise with optimizing 0-1 loss, specifically that it's not continuous. And so often we look for a convex surrogate, and one of these that's often used in practice is logistic loss, which we minimize logistic loss, and it's nice because, again, continuous and convex, and then we usually take the sign of our minimizer, and over the training data, you'll actually get the same prediction or label as you would with 0-1 loss. And so we formalize this by the notion of a property, because in ERM, if you were to get an asymptotically growing data set, you can imagine that as you get more and more data, it models the underlying data distribution. And so here, if we take that distribution P, we want to say that for every probability distribution, we should be able to get the correct minimizer of our loss function. And so we call this property gamma, and it's actually a function from a distribution to a report prediction R. And this can be both in the finite or infinite outcome setting. But here we actually focus on the finite outcome setting, and we say that a loss elicits a property if for every distribution we can express it as the minimizer of this loss. And additionally, we say that the property is elicitable, and then it's convex elicitable if this loss function is convex. And so that's kind of the big question that we're going for here is, when are these loss functions convex? And so kind of giving a cheat to our main result over real valued continuous properties in the finite outcome setting, we know that any property that's elicitable is also convex elicitable, and we do this by reducing to a finite set of functions and then, in a sense, convexifying them, making sure that they still have the same minimizer, and that, to say in ERM terms, they're still minimized by the same hypothesis function, but we are able to actually optimize them in a nicer manner. And this actually has implications in the algorithmic economics literature as well, specifically with a generalization of prediction markets called scoring rule markets. And so that was a very high-level overview, but with that, please, if you have any more questions about intuition details, come visit our poster with any questions or thoughts. Thank you.
Are Ilias, Daniel, or Alistair here? Cool. Cool. So there's one more spotlight.
Thanks for staying. Sorry about the little delay. So I'm here to present this work on sharp bounds for generalized uniformity testing by Elias Diakonikolas, Daniel Kane, and Alistair Stewart. I'm none of these people. I'm the last one. But hopefully I will be able to give justice to the work. So this work is about distribution testing, or if you prefer, hypothesis testing, composite hypothesis testing, which is the general problem of you've given IID samples from some unknown probability distribution, and you want to decide whether it satisfies some specified property of interest. So this was introduced well, a couple years back, 1899, by Carl Pearson, and that person, and is by now a classical problem in statistics with an extensive body of literature. Here are two citations. And over the past 18 years or so, it has been also considered in the context of theoretical computer science under the name property testing for distributions, as introduced by Goldrack-Ron in 2000, and then formally by Batu et al. 1 year later. That's the journal version. So, in a more specific fashion, what is distribution testing? So you've got some discrete domain omega, and you're interested in some fixed property of the distribution. A property is just a subset of distributions, essentially, the distributions that you're interested in. And you're given access to IID independent samples from some unknown and arbitrary distribution, call it P, and some distance parameter epsilon between 0 and 1. And your task is to provide a test which, given these samples, with high probability, will decide correctly between the two cases that unknown distribution as the property of interest is in the class C, or the total variation distance between P and any distribution in that class is at least epsilon. So total variation is also known as statistical distance, and it's basically up to a factor 2, the L1 distance between the PMFs of the distributions. So this is, as I hinted, not a new problem. We've got by now many sample, also you want to be sample optimal and, if possible, to have efficient algorithms. By now we've got many tight results for testing discrete distributions over a known domain of size n. So omega is let's say the integers from 1 to n. And we know to test uniformity, identity, which is goodness of fit, equivalence, two-sample testing. Independence is your distribution a product distribution over, like, let's say, omega square or far from it. Conditional independence, monotonicity, etc., etc. Here are a few citations. I think I'm missing approximately 100. And we're going to focus, as the title hinted, on uniformity. So more specifically again, what is uniformity testing? You're given samples from some arbitrary distribution over the domain omega, and you want to distinguish between the case where that distribution is the uniform distribution on omega, or it's epsilon far from it. Why this problem? First of all, it's a fundamental question. If you can't do uniformity, you can't make it anywhere, basically. And it's been, well, it's a fundamental question. It's been studied quite extensively, and we have by now sample-efficient algorithms which are sample-optimal. Square root of the domain size over epsilon square are sufficient and necessary, which I'm still going to talk about something, though, because there is a catch. This optimal bound is when you know the domain. So you know that the distribution is over a set that is given to you. What is generalized uniformity testing is when you don't know it. You're given samples from some arbitrary distribution, and you want to distinguish between the case like where it is a uniform distribution, or it's far from every possible uniform distribution on this domain you don't know. And indeed, we don't know omega, because in practice, why would you? You're not given, in many cases, you actually don't know a priori the domain of the distribution. So I'm going to try to do it quickly. Is it still the same, or is there a reason for me to talk about this work right now? And the answer is, it's not the same. So in short, with Tukan Batu last year, we had a result showing that in this new question, you actually need dependence on that unknown distribution to do adaptive testing, which is essentially inverse of the third norm of the PMF, which, if you think in terms of domain size, it's going to be n to the 2/3 instead of square root n. And we prove it's necessary.
And in this new work, Ilias, Daniel, and Alistair show that actually the tight expression is this thing, which depends on the 2 and the 3 norm, and that degrades gracefully depending on what your distance parameter is. So if you're interested in knowing more, please come to see at the poster adjacent to 92, because that's where I'm going to be. But to conclude, here are a few remarks. Can we have that adaptive instance optimal setting for other hypothesis testing questions? I.e., can we get instance-specific bounds of that form for all the flurry of citations I had before? And how does this simple estimator that they've got, how does it perform in practice? Thank you.
Okay, so that's the end of the session. Let's thank all the speakers again. And now we have a poster session. Thank you all.